Number 38. A .025 kilogram bullet is accelerated from rest to a speed of 550 meters per second in a 3 kilogram rifle. The pain of the rifle's kick is much worse if you hold the gun loosely a few centimeters from your shoulder rather than holding it tightly against your shoulder. Letter A. Calculate the recoil velocity of the rifle if it is held loosely away from the shoulder. All right, so here's our little picture over here. We have the rifle in black, the bullet in red, and I listed all the knowns and unknowns, right? So we know the mass of the rifle, we know the initial velocity of the rifle, right? Or before the collision, aka the explosion happens, and we're looking for that recoil velocity or the velocity after the explosion happens. All right. Similarly with the with the bullet, you know the mass of the bullet, the velocity before the explosion inside the chamber is 0, and then the velocity after is going to be positive 550 because I chose to frame the problem with the bullet moving to the right. We have seen this pattern a couple of times in the problems before. This is basically an inverse inelastic collision problem. Before an explosion happens, aka the collision, the items are stuck together. And then after the explosion, we would expect if the bullet moves to the right, the gun should move to the left, and that is the recoil velocity. All right, so that's why this is the recoil velocity. That's what I'm looking for. All right, so it's momentum, conservation of momentum. Let's talk about that equation. So the momentum before the collision occurs or the explosion would equal the momentum after. So before it explodes, remember, it's a system that's together, right? So we're talking about the total mass of this entire thing. The items are not separated yet. So therefore, the momentum before the collision or the explosion here would be equal to the total mass multiplied by that initial velocity, all right, before the explosion. And that will then equal the momentums after the explosion happens. Remember, the bullet will be moving to the right and the gun will be moving to the left. And the momentums are a function of mass times velocity. So therefore, the momentum, let's say, of the gun, which I called number 1 here, would be multiplied then by the velocity of that gun after the collision, plus the mass of the bullet, right? And then multiplied by the velocity of that bullet after the collision. Realizing that the velocity before of both items, because they're together, before the explosion happens within the chamber is 0. What happens to this whole term, ladies and gentlemen? That also goes to 0. So that I can cancel. All right, and knowing that I need to solve for the variable I need to solve here is v1a, right? I need to solve for this. I'm going to start to bring this term on over to the left-hand side, okay? So we're going to do a couple of things at once here. So now it would be negative m2 v2a equals m1 v1a, okay? And then divide out the m1, right, from both sides. So our equation now works out to be negative m2 v2a all over m1 would be equal to v1a. And now all we have to do is just plug it on in, right? So let's just move this on up. I think I could fit it right beneath. So let's just plug in the numbers. So m2, the mass of the bullet, is 0.0250. The velocity of the bullet after the explosion inside the chamber is 550 meters per second, all divided by the mass of the gun, which is 3 kilograms. And that will then equal v1a. So let's just plug it on into the calculator. So we got negative 0.025 times 550 divided by 3. And there we go. We get a recoil velocity now of about negative 4.58 meters per second. All right, and that is the recoil velocity of the gun. All right, and why is it negative? Well, we talked about that before. If the bullet's going to move to the right, the gun should be moving to the left, and how I frame the problem. So the way I frame this, the answer should be negative. You might have chosen the gun to go the other way with the bullet starting here, going that way, right? And here's can't really draw to save my life. But then the gun would be moving to the right, and therefore your answer should have been positive, right? But then this velocity would have been negative, and that's how it all would have worked out. Anyway, moving on. So that's I wrote an I down there. I don't know why I did that. That is not initial. It should just be 1. The velocity of the gun after. All right, so it's 4.58 meters per second. So that takes care of letter A, and it was loosely held, so that's why we didn't incorporate any mass of the body at all, right? If it's held tightly against the body, then now all of a sudden you're adding more mass to the system, okay? But if it's loosely held, it's just the mass of the gun that will be experiencing that recoil. All right, letter B. So how much kinetic energy does the rifle gain? Okay, so now if we're talking about how much kinetic energy the rifle gains, specifically just the rifle they're talking about here. Actually, let me just write a little A here, and this will be a little B. All right, so we're talking about kinetic energy. Kinetic energy gain, all right, of the rifle will be equal to the kinetic energy, the final kinetic energy of that rifle minus the initial kinetic energy, right, of that rifle. So expanding this, the kinetic energy gain of the rifle will be equal to the final, okay, which is 1/2, multiplied by the mass of that rifle, multiplied by the final velocity of that rifle, or aka the velocity after the collision, right, or after that explosion, squared, minus then the initial, but remember, kinetic energy is a function of velocity, and the velocity initially for the rifle was 0. So this whole term just drops to 0, so this is my equation. So the kinetic energy, therefore, gained by the rifle will be equal to 1/2 multiplied by the mass of the rifle, which is 3 kilograms, multiplied then by the final velocity, which we calculated, -4.58, and square. So let's just plug it on into the calculator. So we got 0.5 times 3 times negative times negative will cancel out, so I'm just going to write it in as positive in my calculator so I don't have to worry about parentheses and all that stuff. So 31.5. So this works out to be 31.5, and that's in terms of joules. So that's the kinetic energy that the rifle has actually gained. Okay? Now, let's take a look at letter C. What is the recoil velocity if the rifle is held tightly against the shoulder, making the effective mass 28 kilograms? So the setup is literally identical, right? The only difference is now that this mass has changed. So, not a big deal. Everything we just did here is going to stay the same. The only difference shows up down here. Instead of 3, this now becomes 28. Okay, 28. And 0.0 if you like, 28.0. So now we'll calculate the new, so this is letter C. This will be the new V1A. And let's just calculate that. So -0.025 times 550. And that will be then divided by 28. So here we get a value of -0.491. -0.491 meters per second. Okay, it's still negative because it's still going to be moving to the left after the collision. And but notice how much less it is. I mean, we're talking significantly less, right? So let's see what they're going to ask for D now. How much kinetic energy is transferred to the rifle shoulder combination? All right, so letter D, let's write it over here. So basically we're going to do a similar approach. So notice that the velocity then has changed. Okay, so when we think about now the kinetic energy, transferred to the rifle shoulder combination, we're basically going to do the same process as we did for letter C. We're just going to manipulate the numbers in this equation. All right, so two things though have changed, right? The mass, it's not only the mass of the rifle anymore, now it's the mass of the rifle shoulder combination. So instead of it being 3, the operative mass here will be 28. And along with the velocity here, the velocity now is no longer 4.58. It is now going to be -0.491. Don't forget to square that. And now when we do the math, we can just plug that on into the calculator, right? So the kinetic energy here will be equal to 0.5 times 28 multiplied by negative, right? Negative times a negative will be a positive, so I'm not even going to bother plugging that in. So 0.491 squared. And we get a value of about 3.38. So we got 3.38, and that is in terms of joules. All right. So now if we just look at, a simple ratio here, let's do 31.5, which was the original kinetic energy of the loosely held gun, and divide it by 3.38, which is the now the rifle shoulder combination. And we notice that, before by holding it loosely, it's 9 times greater. This value is 9 times greater than this value. So therefore, if pain is, because they're talking about pain here, right? The pain is related to the amount of kinetic energy. So if it's, directly related and linearly related, the kinetic and the pain here for the gun loosely held would be 9 times greater than the pain that's experienced when you tightly hold the gun. All right. So that takes care of that. And then what do we got for letter E? It says calculate the momentum of a 110 kilogram football player running at 8 meters per second. Compare the player's momentum with the momentum of a hard thrown 0.41 kilogram football that has a speed of 25 meters per second. This sounds very, very similar, actually identical to a question we've done. I think it's number 33. So I'm just going to write here scene number 33 in this chapter for a discussion on letter E. Totally solved that, complete. So that should provide the necessary help for you guys if you need help on letter E. And it says discuss the relationship to this problem. You'll totally see the relationship after you watch that video. I think I laid it out fairly clearly. So guys, thank you so very much for tuning in. Please remember to hit that subscribe button. I look forward to helping you out with the next question. Take care.